In the last video, we talked about an equilibrium system where you've got these reversible reactions. At the same rate that the reaction is going forward, those products are also going backwards and reforming the reactants. If it's truly at equilibrium, the rate of the forward equals the rate of the reverse. Systems want to be in a state of equilibrium. However, we can do something to send that system out of equilibrium by changing the conditions. And our options are like, we could change the concentration, we could change the pressure, we could change the temperature. And that might send this reaction in a little bit of a tizzy. It sets it out of equilibrium. So this LeChateliers principle explains that if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change. So if I do something to alter the conditions and I send this system out of equilibrium, it's not happy as if it has feelings, but it's not stable. These systems want to be in equilibrium. So we're going to make a little shift. We're either going to shift forward or reverse, and we're going to try to bring conditions back to equilibrium. We're going to try to reduce the change that we imposed on the system. One of the most common options is this first one. If we change the concentration of something, what if we increase the concentration of a component? So let's say I have this fake reaction, and we can just call it like A plus B, and we'll go a double-sided arrow to show that it's an equilibrium system. We form C and D. All right, so let's say I increase the concentration of A. The reaction is at equilibrium if we have the ratio from the balanced equation present. If it's going forward and reverse, we should have everything present at a 1-to-1 ratio in this particular balanced equation. So what if I add extra A? So now maybe I have 2 moles of A. I don't want 2 moles of A, I want 1. I want this ratio from the balanced equation. So if you add something, you increase the concentration of one of the components. The equilibrium will shift in the direction that consumes whatever was added. Or to simplify that, I always think like shift away from what was added. What was added? Oh, come back to me. There we go. So for example, let's say we add A. Then we're going to shift forward. We're going to shift away from A. We'll shift in a direction that consumes it, that makes A a reactant. On the flip side, if I would add extra D, let's say, I don't want extra D, I want 1 mole of D. So now we're going to send this thing in reverse. We're going to favor the reverse reaction that again would put D kind of as a reactant. If I was favoring the reverse reaction, we would try to consume the extra D. The opposite is true if you decrease the concentration of a component. If I decrease something, I'm going to shift to produce more of whatever was removed. So we'll say shift toward what was removed. What was removed? We want to replace it. So for example, if I take away A, I want 1 mole of A in this particular equation. What if I reduce that to like half a mole? Well, then we're going to shift reverse. We're going to shift toward A so that we can produce more A. If I remove a product, we'll shift more forward. We'll shift in a direction that produces more of one of these products, C or D. Some examples. Here's this fabulous equation. Now, they'll usually give you the balanced equations here. We're going to predict the direction of the shift. Your answers here are either going to be forward, reverse, or you could say like right, left. Like in what direction will the equilibrium shift? What direction will we favor in order to take care of this change that we've opposed on the system? So if I add extra carbon monoxide, we find carbon monoxide, it's a product. It's on the product side, I should say. So if I add extra carbon monoxide, I want to shift away from what was added. So we would say this would shift in reverse. I add extra carbon monoxide. I want to use it up. So we'll shift in reverse. We'll shift opposite what you added. If I add something on the reactant side, so here I'm adding some of this arsenic oxide. That looks yummy, right? Not. Let's shift forward. We'd shift away from what was added. So if we add a particle that's on the reactant side, we'll shift more forward. If we remove something, in this case we're going to remove arsenic. If I remove arsenic, I want to shift to replace it. We would call that forward. Oh, cool. If I remove something on the reactant side, let's say we remove carbon, again, like we want 6 moles of carbon, so if I did something to reduce that, I'd want to try to bring it back to this ratio in the balanced equation. So we would shift reverse. Oh, okay, that's not so bad, right? We're shifting toward whatever was removed. We're shifting opposite something that was added, away from whatever was added. Another option, which is actually kind of along these lines, if you change the temperature, that can affect the system at equilibrium. Think about temperature as like an energy value, and sometimes they'll have it written in the equation. There's a few different ways they could show it. So here's this fabulous equation with some nitrogen, oxygen gases. They might say plus, in this case, 58.8 kilojoules. So in the forward direction, it's exothermic, producing 58 kilojoules. In the reverse, it would be endothermic. Going in reverse, we would absorb the 58 kilojoules. Sometimes they might do this. They might just say like plus energy. So they might just write in the word energy. Maybe they don't have the specific amount of energy. Or another option, they might just list this like over here. They might say like delta H equals negative 58.8 kilojoules. Showing that in the forward direction, we release 58.8 kilojoules. All of those are just a way of showing the energy value of this reaction. So then if you do something like increase the temperature, think about that as if you were adding energy. Oh, well then we can kind of treat it the same way that we were treating like an increase in concentration. If I add energy, here's the energy component. It's exothermic going forward. I want to produce 58 kilojoules, but no more than that if it's at equilibrium. So if I add extra energy, I want to shift in the endothermic direction. I want to shift reverse. We'd shift away from what was added. In this case, it's energy by increasing the temperature. If I decrease the temperature, it's like I'm removing energy. So now I want to shift in the exothermic direction, which in this case is forward. I would shift more forward. So again, think about an increase in temperature or a decrease in temperature as if you were adding or removing energy. And then it'll follow the same rules as that concentration change. The last option that we can do to change conditions would be to change the pressure. So now this is usually a system that's going to have a lot of gases or maybe like liquids or solutions, particles that can move, that would be affected by a change in pressure. Probably not a lot of solids. The pressure change really might not have a huge effect on a solid, but it would on a gas or a liquid or particles in solution where there's more space between the particles that they can flow better. If I change the pressure, for example, let's say you increase the pressure, we try to relieve the pressure. One option is to favor the side with less particles. If you have less particles, that should mean less collisions. If there's less collisions, that should mean less pressure. So keeping all conditions the same, all other conditions, like we're not going to also change the temperature and the pressure. We only change one variable at a time. If I look at this reaction here, I've got brown nitrogen dioxide and a colorless dinitrogen tetroxide. If I look at the mole ratio, it's a 2-to-1 ratio. So if I were to increase the pressure, I would favor the side with less total particles, which in this case would be forward. Now also in this reaction, you should notice a change in color. It should get lighter. Oh, if you're shifting forward to form less particles, which should help to relieve the pressure, you're shifting toward that colorless gas. So it should get lighter. Now when this thing is at equilibrium, there's nothing that's a zero. It's not like it just goes forward, makes colorless gas, and done. If that were the case, it would be completely colorless. It's always going to have this reversible arrow. So there's, like, at equilibrium, 2 parts brown gas, 1 part colorless gas. All components are present at equilibrium, and they're present at the ratio from the balanced equation. So at equilibrium, this kind of looks like a, I don't know, kind of a light brown color. But as I shift forward, I should see it turn a little bit lighter until I reestablish a new state of equilibrium. And eventually, the color will become consistent again. Cool. Now, what if I had a system that had like 2 particles on both sides? What if the mole ratio was like 2 to 2? Then a pressure change really won't affect the equilibrium. Oh, interesting. So we're really looking for the side with less particles, and if there is no side with less particles, then changing the pressure really has no major effect on the equilibrium system. Now, we could argue in this case for temperature. You know, going forward, I'm producing energy. And so like, if by chance I had the same amount of particles on both sides, so I had something kind of like, 2A, and I had something like this, 2B plus energy. If I had the same amount of particles on both sides, and if I did have an energy component, and I increased the pressure, could I maybe then shift away from energy? Yes. If I shift away from energy, which in this little example would be reverse, if I have less energy, then the particles have less kinetic energy, which would make less collisions, or maybe less forceful collisions. And then, yes, that could help to alleviate the pressure. Now, if you didn't have that energy component, then you would have no choice but to say no change. If it was just 2A and 2B, and we didn't know the energy value, then we would say changing the pressure would have no effect on the equilibrium. But if it was equal moles of particles on both sides, and one side was exothermic, we could shift away from energy. Because then again, by shifting away from energy, the particles would have less kinetic energy, which would maybe cause less forceful collisions. Alright, so this one's cool. Check out this guy. I like this example. There's like everything you could ever ask for in this one example. This is kind of what you'll end up doing in the lab. You'll be able to predict your observations after inflicting change on an equilibrium system. Excellent, can't wait. And then you'll go in the lab and actually try these changes and see if your predictions are right. Now, on paper, we might just predict forward reverse, but in this case, we've got some color changes again that we might predict what we would observe if we did this in the lab. If it shifts more forward, it might turn more blue. If it shifts more reverse, it might turn more pink. Let's do some easy ones first. How about D and E? Let's do the temperature change. If I increase the temperature, it's like adding energy. So I'd want to shift away from energy. If I'm shifting away from energy, that's forward. In the lab, I might see it turn more blue. Cool. I'm shifting toward the blue particle and the colorless particle. I should see more blue. If I decrease the temperature, I'd want to shift to replace energy. That would be a reverse. If I'm shifting in reverse, I should see it turn more pink. And then we can run this in the lab and see if our predictions are right. What if we do the pressure change? If I increase the pressure, I'm looking for the side with less particles. So I look at the mole ratio. Here's 1 and 4. There's 5 particles on the reactant side. And there's 1, 6. There's 7 particles on the product side. 5 particles on the reactant side. Versus 7 on the product side. If I increase the pressure, I'm going to shift reverse. I'd want to shift in reverse toward the side with less. Now, in this case, not only might I see pink, but do you also notice, like, if I'm shifting in reverse, and I'm not monkeying with the temperature, do you see one of the other components is energy? It should get warmer. Like if you feel the outside of your test tube or your beaker, if you're shifting toward energy, that's the exothermic direction. You should feel that energy released. Ah, cool. If I'm shifting this thing more forward, I'm shifting in the endothermic reaction. I might feel the outside of my beaker or test tube be a little bit cooler. Okay, so now let's hit these other ones. If I add water, water is on the product side. I'd want to shift away from water, which would be reverse. So again, I might see it turn more pink. I might feel the outside of the test tube or beaker. It might feel warmer. How about we hit A? If you add chlorine ion. All right, so here's the chlorine ion. It's on the reactant side. If I add more chlorine, we're going to shift more forward. As I shift more forward, again, it should look blue. It might feel cool. It would be more blue. It might feel cooler. As I shift away from energy. And if I remove chlorine, I'd want to shift to replace chlorine, which would be in reverse. So if I'm shifting in reverse, I should see pink. And I might feel it be a little warmer. Okay, now let's look at A and B a little bit. Realistically, how do you do this? How do you add and remove chlorine? Well, the addition of chlorine, that one's a little easier. All I have to do is add some kind of a chlorine solution. A solution that has chlorine ions, as long as the other ion is a spectator. The other ion cannot react with anything in the system, and it can't be something that's present in the system. So, for example, good examples might be like a sodium chloride solution. You could add aqueous sodium chloride. You could add maybe like some hydrochloric acid. Where both solutions will have chlorine ions, but in both cases, the sodium and the hydrogen are spectators. Spectator ions. Blast from the past. The sodium and hydrogen are not present in this reaction, and they can't react with anything in the reaction. So they're complete spectators. It's just the chlorine ion that will affect this equilibrium system. Now on the flip side, how do you remove chlorine? What do you like, go through and try to pick them out? It's not like you can filter out chlorine ion. So one option is to form a precipitate. Form a chlorine precipitate, because now you don't have chlorine ions in the solution. They're going to sink to the bottom as some kind of a chloride compound. A good example might be this guy. Add something like silver, maybe silver nitrate. If you add silver nitrate, the nitrate is a spectator. It's not present anywhere in that equation, and it can't react with anything. I mean, anything with nitrate is aqueous, so it's going to stay a solution no matter what. However, when the silver ions react with chlorine, they're going to produce a precipitate. So again, now you're not letting those chlorine ions swim around freely in the solution. They're going to bond with silver, drop to the bottom as a solid precipitate. You could do this with something like lead nitrate. Any chloride that would be insoluble, so like lead chloride, would be an insoluble compound. So to remove an ion, make it a precipitate. Think of something that you could add that would form an insoluble compound with whatever you want to remove. Otherwise, like if you really grasp this concept of LeChateliers Principle, we can apply it to so many different situations. I mean, these equilibrium systems are actually really common. So if we do something to change the concentration or change the temperature, change the pressure, we can predict in what direction this reaction will favor in order to get back to a state of equilibrium. Happy reactions, that's what we're looking for.